The first set of operations that we're going to learn how to do with matrices is addition and subtraction, and this is a very straightforward process. Now, the first thing that you've got to know is that matrices must have the same dimension for you to add them and subtract them. And the reason for that is because we're going to identify each individual place of the matrix, and we're going to add or subtract that particular spot on each one of them. And so you can see here in example 1, what I've done for you is I've actually color-coded the individual cells or the individual locations of each of the numbers according to their row and their column. And so you can see here in part A, we have 3 rows and one column, So we have 3 rows by 1 column, and we're adding it to 3 rows by 1 column, and so that checks off. Now, if we did not have a situation where the dimensions were exactly the same, we just basically couldn't perform this operation, and so there would be no answer for us. Now, you can see that the 3 and the 1 are both in the first row, first column, and so I've color-coded those with a blue so that you could see that addition of 3 plus 1 and 4. And then we've got the rest of the parts of the matrix, and you can kind of follow along according to the color coding. Now, in part B, we have a little 2 by 2 matrix, and we're subtracting a 2 by 2 matrix. And of course, you can see I have an 8 and a 2, and then I'm subtracting. So 8 minus 2 is simple enough. Now, notice the red numbers, the 3 and the negative 7. We have to remember that if we're subtracting a negative number, we should put those negative numbers in parentheses, because that 3 minus a negative 7 becomes addition, and then that would be 10. And so you can see how that would work. So this is a very straightforward process. You just have to be very aware of the dimensions and the individual parts matching up to each other, and sometimes we call those corresponding parts. Very similar to what you learned in geometry in relation to polygons. So let's move on down to a sample problem. And so you can see here, sample problem number 1, you have 3 calculations to make. Let's go ahead and pause the video right now and try to work those 3. Okay, so hopefully you were able to do that. I'm just going to go ahead and work each one of these individually. So we can see here that first of all I have 3 rows, 1 column, 3 rows, 1 column. That lets me know that I can add the individual parts, and so then I'm going to do that. 0 plus 1 is 1. 4 plus a negative 9 is going to give us negative 5. And 3 plus 8 is going to give us 11. And I'm going to use these little square brackets. And that gives me a 3 by 1 matrix, just like the other matrices were. And so that's how that should come out. Okay, and now we have a 2 by 2 subtracting a 2 by 2, so that's going to be okay for me to do. So I'm going to do 3 minus 2, which is going to give me 1. I'm going to do 3 minus 0, which is going to give me 3. And it really doesn't matter what order I do these in, as long as the location is correct. So 9 minus a negative 3. That's the same thing as 9 plus 3. It's going to give me 12. Now I have negative 5 minus 5, which is going to give me negative 10. And I square that off with our matrices. You can see that's a 2 by 2 matrix, which is exactly what we should have expected. And then this last one, we can see we have a 2 by 2 matrix, but then we have a 2 by 1 matrix. And this right here should tell us very quickly, since our matrices are not the same dimensions, we cannot perform this operation. And you could write your answer in any number of different ways, as long as we get the idea of what you're trying to create there. Let's look at one more type of operation here. This next operation is called scalar multiplication, and the reason we call it scalar multiplication is because the scalar is really kind of like just a multiple. We're not multiplying 2 separate matrices at this point. We're really just multiplying one singular number times an entire matrix. Now this has a similar effect of the distributive property. So if you look here at example number 2, we have a 3 that's being multiplied times this entire matrix. So what that means is I need to multiply the 3 times everything in the matrix, and so it kind of distributes to every part of the matrix, and you can see our second step here, we've done that. And then we get a resulting matrix. Okay, so that's pretty straightforward enough. So why don't you go ahead and try to work sample problem 2. We start with a scalar multiplication, and then in part B we put all of it together. Alright, so go ahead and try that now. Okay, so we come back here and we see that we have 6 times everything inside there, and so I'm just going to multiply 6 times 2, which gives me 12, 6 times 8, which is 48, 6 times negative 3, which is negative 18, 6 times 4, which is 24, and our matrix should be the same dimensions as the previous matrix. Alright, now this last one, you kind of have to deal with order of operations similar to the way you would with real numbers. And so I have to do the scalar multiplication before I can do the addition. So I'm going to go ahead and multiply negative 2 times everything inside the first matrix. And notice I'm only multiplying negative 2 times the first matrix. There's no parentheses or anything that would imply that I'm doing it to both matrices. So I've done the scalar multiplication, and then I can do the addition of those two. Now, if you did all this in your calculator, that's absolutely fine. Just make sure you understand the principles behind why it works and how it works, just in case you get in a situation where you're not being allowed to use your calculator.